Greetings and welcome to Unit 2. We're going to have some rip-roaring fun this unit, learning functions and their graphs. Seriously, it's pretty cool and it won't be that bad. I think you will enjoy. Since this is our first instructional video together, I want to remind you that you should be watching this video with your notebook and a writing utensil, taking notes as needed. Please make sure you utilize the pause button in the event that you need to write something down before you proceed with the video. Also, feel free to use the rewind button in the event you want to rehear something I said or view again something you saw in the video. And you can also use the mute button in the event you want to try to see if you know how to do something without hearing me with the explanation. And there's always the fast forward key in case you're done hearing me. So let's proceed with our first lesson in this unit, where we're going to talk about an introduction to functions. We're going to start by the idea of relationships or relations. And something that you know is relationships with the people in your life. So you have a relationship with your parent. There's a parent-child relationship. You have relationships with your siblings if you have them, a sister or brotherly relationship with them. You can have a best friendship, or maybe you have a group of friends that you bum around with. And so you have that special relation with those people. Sometimes you just have what I call just regular friendships, people that you still maybe see inside and outside of school. Maybe you're not as close to them. And then you have acquaintances, those people that you might see around school or people at work where you kind of know them. Maybe you know their name, but maybe you don't know them in depth very well. And then there's romantic relationships, boyfriend and girlfriend relationships. So those are just some different types of relationships you have. So now I want to turn that thinking and think about what are the relationships that you have in math. So here are a few that I came up with just to kind of get the ball rolling. You can think about there's a relationship in the universe when you see in a community a decline in jobs and the number of home foreclosures. People don't have as much money because they don't have a job and they can't afford their homes. That's a mathematical relationship. We can use this as a graph. We could represent it by a table. We can look at the percentage or the unemployment rate percentage, as well as the number of home foreclosures, and make those mathematical relationships. The mortality rate versus the availability of vaccines, especially if you go to poorer countries where the death rate is much higher than our modern society in the United States. A lot of times you'll find that the availability of vaccines just isn't there like it is for us at our local doctor's office or down the street at Walgreens. So their death rate might be higher. Another mathematical relationship that occurs in the universe is maybe an increase in gas prices versus shipping costs. If you're like me, I like to online shop and I always try to get free shipping. Usually you have to purchase so much in order to earn that. Sometimes depending on how much money you spend, depends on the number or the amount of shipping costs you pay. And even if you go to a traditional brick and mortar store, you're going to the mall, they're building those shipping costs within the price of whatever you're purchasing at that store. So as gas prices go up, you'll find that groceries, clothing, toys, video games, all those kinds of items can increase in cost. Data usage versus the cost of your cell phone bill. Some of you might just have a flat fee that you pay each month and you have unlimited data usage. Others of you might be limited to 4 gigabytes, or maybe you share with your family. And I'm sure if you go above that, your parents will say something to you because the cost of your cell phone bill is going to increase once you exceed the cost or exceed the amount of time that you've used on data on your phone. Another relationship is the number of miles driven versus the cost in fuel. I went on a vacation this summer. We drove 3,500 miles. So obviously, as we drove more, our gas cost for that vacation increased because we had to buy more gas for our road trip. So the mathematical term for a rule of correspondence is a relation. We can relate anything we need to. I grew up in farm country, so they might relate the inches of rainfall with how tall the corn stalks are, so they can determine, hey, when do we think we're going to be able to harvest? Might not be exciting or meaningful for you, but it sure is for those in the farming industry. Those are relations. But a special type of relation is called a function, and here are some working definitions. The simplest, the one that you'll hear me say in class often, is just for each input, there's exactly one output. Think of your average in school. Regardless of how your teacher calculates it, you input your grades. You mathematically compute your average. One average comes out. You don't want 3 averages to come out and the teacher make a subjective decision on which grade you should have. Input grades, output 1 grade. Another workable definition is each item from one set will pair with exactly one item from a different set. The one the book gives, which is a little bit wordy, a function f from a set A to a set B is a relation that assigns to each element x in the set A exactly one element y in the set B. Blah. Okay, let's talk about that one a little bit more in depth. Here are the four characteristics of a function. Each element in A must be matched with an element in B. What does that mean? Well, let's check it out. I have an example for you. Okay. If each element in A must be matched with an element in B, notice how each element in A represents time of day in the afternoon. Element in B, the B set represents your temperature in degrees or your output or your range values. And notice how at 1 o'clock the temperature is 9 degrees Celsius. At 2 o'clock it's 13 degrees Celsius. At 3 o'clock and at 4 o'clock it's 15 degrees Celsius, and we'll talk about what's happening there momentarily. At 5 p.m. it is 10 degrees Celsius, and at 6 p.m. it is 12 degrees Celsius. Every time of day has a temperature. Now, if I would put 7 in the box where it does not have a match, then this can no longer be a function. Every member of the domain has to be paired with a member of the range. So having a random domain member is not a characteristic of a function. Secondly, some elements in B may not be matched with any element in A. So if you notice in the range, the numbers 1, 2, 3, 5, 4, 6, 7, 8, 16, 14, and 11, they don't have a match. It's okay. Some elements in B or the range may not be used, and that is still okay to be a function. Characteristic 3, 2 or more elements in A may be matched with the same element in B. Here's what's going on at 3 and 4 o'clock. Sometimes in the afternoon you don't have a change in temperature. So it's okay for the 3 to be paired with the 15 and the 4 to be paired with the 15, because the idea is at 3 o'clock still only one temperature is outputted. And at 4 o'clock only one temperature is outputted, even though it's the same temperature. The ones you have to watch for would be a problem like, or would be a characteristic 4. If an element in A, the domain, is matched with two different elements in the range, it is not a function. So at 6 o'clock, we have it paired to 12. If we also paired 6 p.m. with 10 at the same time, this is no longer a function, because at 6 p.m. we shouldn't have to choose if it's 10 degrees Celsius or 12 degrees Celsius. It's one temperature. Certainly time fluctuates, temperature fluctuates with time. So at 6:01 or at 1 second past 6 p.m., the temperature can change. But if we're looking exactly at 6 p.m., there should output one temperature in order for there to be a function. So this function can be represented by the following ordered pairs. 1, 9, which represents at 1 p.m. we have 9 degrees Celsius. 2, 13, which at 2 p.m. we have 13 degrees Celsius. At 3 and at 4 p.m. we have 15 degrees Celsius. At 5 p.m. we have 10 degrees Celsius, and at 6 we have 12 degrees Celsius. So we can take this mapping, this picture, and rewrite it as a set of ordered pairs. Remember that strategy in the event a problem is presented as a mapping if it doesn't make sense to you. There are 4 ways we can represent a function, and this is where we dang it. You should be able to talk about a function descriptively, which means we use things like sentences to describe how the input and outputs are related. We can also, the A and dang it is you have to be able to represent a function algebraically, and usually this is in the form of an equation. So you should be pretty familiar with equations such as y equals 3x plus 2. So that equals is what makes that the equation. The N in dang it is for numerically. So when in doubt, T-chart or make a table it out. Make a list of ordered pairs of input and output values in a chart. You can also do a set of ordered pairs like we had in the previous slide, but that's what we mean by numerically. And then graphically, it's where we plot points on a graph in a coordinate plane, where the horizontal axis is your, the input values are on the horizontal axis and the outputs are on your vertical axis. So how do we test for functions? You have to be able to test for functions descriptively, algebraically, numerically, and graphically. On this video, we'll talk about descriptively and algebraically, and then when we come back together for class, we'll talk about the numeric and the graph. So let's test for functions from a descriptive perspective. First example, the input value x is the number of West High students and the output value x is the number of cars parked in the upper lot in the pit. This is a function. Why? Well, the number of cars is dependent on how many students are driving and arriving to school. So if you think about the end of the school year, the seniors leave early since they graduate. And so the number of cars parked decreases because the number of students at school decreases. Now, I realize that it might not decrease by the entire senior class because more sophomores who have their license by that time might drive. But in general, there's a lot more parking spaces available that last week of school than there was the remainder of the year. So it is a function. Let's look at example 2. A person's height is a function of their weight. This is not a function. Here's why. In general, the independent variable in this case would be height. We determine a person's ideal weight based on their height, not weight determining height. So for instance, if it was a person's height is a function of their weight, we would be saying that everybody who was 120 pounds would be 5'2". Rather, we would input 5'2", and we would say that this weight is an acceptable ideal weight for that height. So in general, we always talk about height being the independent variable and weight being the dependent. Next, we're going to talk about it algebraically. Which of the equations represents y as a function of x? Keep in mind for each input there's one output. So what do you need to do on your paper? You need to solve for y. So let's look at problem A. If I have x plus y equals 7 and I solve for y, I would subtract x from both sides to yield y equals negative x plus 7. This is a line. This is a function because every x input is going to have one output. However, let's look at B. If I solve for y, I'm going to add x to both sides, which yields y squared equals x plus 4. Then I'm going to take the square root of both sides. And when I take the square root of both sides, you end up with plus or minus radical x plus 4. So for instance, let's x be 0. If I put in 0, I would get the square root of 0 plus 4, which is 2. But then I would also get the opposite of 2. So this is not a function because if I input 0, I would get either 2 or negative 2 or more than one output. Part C, the absolute value of x minus y equals 5. So I am going to subtract absolute value of x from both sides. Then I'm going to divide each side by negative 1, yielding y equals the absolute value of x minus 5. And this one you have to think through. And I think the easiest way to think through it is maybe just through a table. If I input the number 2, the absolute value of 2 is 2, minus 5 gives you negative 3. That's only one output. Life is good. If I put in negative 2, its absolute value is positive 2, and the output is negative 3. So again, it's okay by the characteristics of functions for 2 and negative 2 to share the output negative 3. It just would not be okay if the number 2 had 2 outputs. So C is a function. At this time, you can stop the video. Hopefully you learned a thing or two, and when we come back together, we will do a TI Inspire lab on our calculators to talk about how we test for functions numerically and graphically.